Somewhere in the universe right now, a star is dying. Not slowly. Not peacefully. It is exploding, tearing itself apart in a cataclysm so violent that for a brief moment it outshines every other star in its galaxy combined. And when the smoke clears, when the outer layers have been blasted into space, what is left behind is something that should not exist. Something so dense, so extreme, so fundamentally alien to our everyday experience that even the scientists who study it have to remind themselves it is real. A black hole. A place where gravity has become so powerful that the very fabric of space and time folds in on itself. A place where the laws of physics as we know them break down entirely. A place from which nothing, not matter, not energy, not light itself, can ever escape. And here is what should unsettle you most: there is one at the center of our own galaxy. Right now. A million times more massive than our Sun, lurking 26,000 light-years away, silently shaping the fate of everything around it. We used to think black holes were theoretical. A curiosity of mathematics. Something that probably existed somewhere out there but that we would never be able to actually study or see. We were wrong. In the last decade alone, we have detected the gravitational waves produced when two black holes collide. We have photographed the shadow of one. We have tracked individual stars orbiting the one in our own galaxy and watched them move at speeds that defy imagination. Black holes are no longer hypothetical. They are the most extreme, most awe-inspiring, and most consequential objects in the known universe. And we are just beginning to understand them. So today, we are going all the way in. From the violent death of a star to the slow quantum evaporation of the last black holes in a dying universe, this is the complete story of black holes. Every chapter. Every layer. No shortcuts. Stay with me. Because what you are about to learn will change how you see the universe forever. And before we dive in, thank you. Thank you for being here on Orbiting Truths. If you are new here, this channel is dedicated to exploring the universe with the depth and honesty it deserves. No fluff, no clickbait, just the real science explained as clearly and as compellingly as we can make it. If that sounds like your kind of place, you are in the right corner of the internet. Now let's get into it. Here is how today's journey is going to unfold. We begin at the beginning, with the death of a star. Because every black hole starts somewhere, and the story of that birth is one of the most violent and dramatic events the universe is capable of producing. From there, we will explore the event horizon, the point of no return, and what it actually means for something to cross that boundary. We will talk about the mathematics that describes it, the physics that defines it, and the strange experience of what it would be like to fall through one. Then we look at what survives the collapse. Black holes, it turns out, are the simplest objects in the universe, defined by just 3 numbers. We will explore why that is, and why it leads to one of the deepest unsolved problems in all of physics. After that, we explore what happens when a black hole spins, and almost all of them do. Spinning black holes warp the universe around them in ways that even Einstein found hard to believe, and they can actually give energy back to the universe under the right conditions. We will talk about what happens if you get too close, the grotesque and fascinating process by which tidal forces stretch you into something unrecognizable. Then we look at how black holes feed, the magnificent structures that form as matter spirals in, heating to temperatures millions of times hotter than our Sun, producing the brightest sustained light sources in the observable universe. From there we zoom out to the monsters. The supermassive black holes that lurk at the centers of galaxies, including our own, with masses that strain the limits of comprehension. Then we cover one of the greatest scientific achievements of the 21st century, the detection of gravitational waves from colliding black holes, and what it opened up for our understanding of the cosmos. We look at the first image ever captured of a black hole, and what it took to make that image possible. And finally, we ask the deepest question of all: do black holes last forever? The answer, thanks to the work of Stephen Hawking, is no. And the reason why leads us directly to the frontier of theoretical physics. 10 chapters. 1 story. Let's begin. To understand a black hole, you have to understand what it is born from. And that means starting with stars, not ordinary ones, but the giants. The monsters of the stellar world. Our Sun is a fairly average star. It contains enough hydrogen fuel to burn for about 10 billion years, and when it eventually dies, it will expand into a red giant, puff off its outer layers, and leave behind a dense, cooling remnant called a white dwarf. Dramatic by human standards. Utterly unremarkable by cosmic ones. But now consider a star with 20 times the mass of our Sun. Or 30 times. Or 50. These stars are fundamentally different creatures. They burn through their fuel at a ferocious rate, not because they are larger, but because the gravitational pressure at their cores is so immense that nuclear fusion runs at a pace that would seem almost reckless. Where the Sun burns hydrogen for billions of years, a star with 20 solar masses might exhaust its hydrogen core in just a few million years. In stellar terms, that is practically instantaneous. But these stars do not stop at hydrogen. When the hydrogen in the core runs out, the core contracts and heats up until it becomes hot enough to fuse helium into carbon and oxygen. Then the carbon fuses. Then the neon. Then the oxygen. Then the silicon. Each step in this chain requires higher temperatures and produces less energy per reaction than the step before. The star is sprinting through its fuel reserves, burning heavier and heavier elements in its increasingly frantic attempt to hold itself up against its own gravity. And then it reaches iron. Iron is where the music stops. Every element up to iron releases energy when it is fused. That energy is what creates the outward pressure that holds the star together. But iron is different. Iron sits at the bottom of the nuclear binding energy curve. Fusing iron does not release energy. It absorbs it. When a massive star builds up an iron core, and the process happens quickly, over just a matter of days, there is no more energy to be had. The outward pressure disappears. And gravity, which has been held at bay for millions of years, wins. What happens next unfolds in less than a second. The iron core, roughly the mass of the Sun, compressed into a sphere about the size of Earth, collapses. But it does not collapse gradually. It falls inward at a quarter of the speed of light. In a fraction of a second, the core has shrunk from Earth size to roughly the size of a city. The density becomes so extreme that electrons and protons are forced together, creating neutrons. The core becomes, in essence, a single enormous atomic nucleus, a neutron star. But neutron matter is almost incompressibly stiff. The collapse bounces. The infalling outer layers of the star slam into the newly formed neutron star and rebound outward in a shockwave of almost inconceivable violence. At the same time, an extraordinary number of neutrinos, ghostly, nearly massless particles created in enormous quantities during the core collapse, blast outward through the star, depositing energy into the shockwave and helping drive it outward. The result is a supernova. The outer layers of the star are expelled at velocities of tens of thousands of kilometers per second. The explosion is so bright that for weeks or months, a single dying star can outshine the combined light of hundreds of billions of other stars in its galaxy. The material that is blasted outward will eventually form new nebulae, new molecular clouds, and eventually new stars and planets. The heavy elements forged in the star's core, the iron, the nickel, the gold, the uranium, are scattered across light years of space to be incorporated into the next generation of worlds. Everything that was not in the core is gone. And the core, what is left of it? For stars below a certain mass, the core stabilizes as a neutron star. Dense, exotic, fascinating in its own right, but stable. For stars above roughly 20 solar masses, the mass of the core is too great. Not even the pressure of neutron matter can halt the collapse. The neutron star itself collapses further. The density climbs toward infinity. The gravitational field around it becomes so extreme that it warps space-time into a closed surface, a region from which nothing can escape. A black hole is born. In the span of milliseconds, something that was a star, a vast, luminous sphere of plasma millions of times larger than Earth, has become a point of effectively infinite density, surrounded by an invisible boundary beyond which the laws of physics as we know them cease to apply. It is one of the most violent, most extreme, and most consequential events in the universe. And it happens somewhere in the observable universe roughly once every second. The term event horizon is one of the most evocative phrases in all of science. It captures something real and profound. It is a horizon in the same sense that the horizon on Earth is a horizon. From your position, you cannot see what lies beyond it. But unlike the horizon on Earth, which you can walk toward, and which recedes as you approach, the event horizon of a black hole is a boundary you can cross only once, in only one direction. Understanding what the event horizon actually is requires letting go of some intuitions that served us well for most of human history. Think about escape velocity. To launch a rocket from Earth's surface and send it out into space, never to return, you need to give it enough speed to overcome Earth's gravity. That speed is about 11 kilometers per second. Different planets and stars have different escape velocities, depending on how massive and how compact they are. Now imagine compressing a mass into a smaller and smaller volume. As the object gets smaller, its surface gravity increases, and the escape velocity from its surface climbs. For a neutron star, with roughly the mass of the Sun compressed into a sphere about 20 kilometers across, the escape velocity is already around half the speed of light. Keep compressing. The escape velocity keeps climbing. Eventually, you reach a radius at which the escape velocity equals the speed of light. At that radius, not even light, the fastest thing in the universe, can escape. That radius is the Schwarzschild radius, named after Karl Schwarzschild, the German physicist who found the mathematical solution describing it in 1916. Schwarzschild derived his solution directly from Einstein's equations of general relativity, and he did it in extraordinary circumstances. He was serving on the Russian front during World War I, and he solved one of the most complex equations in mathematical physics while dying of a disease he had contracted in the field. He sent his solution to Einstein, who was astonished. Schwarzschild died just months later. The formula Schwarzschild found is deceptively simple. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For our Sun, with its mass of roughly 2 times 10 to the 30th kilograms, the Schwarzschild radius is just under 3 kilometers. Compress all of the Sun's mass into a sphere less than 3 kilometers across, and you have a black hole. The Sun's actual radius is nearly 700,000 kilometers, so we would need to squeeze it to less than 1/200,000th of its current size. For Earth, the Schwarzschild radius is about 9 millimeters. A marble. Compress all of Earth into a marble, and it becomes a black hole. This linearity is important, double the mass, and the Schwarzschild radius doubles. A black hole with a mass of 10 billion suns has an event horizon 10 billion times larger than the Schwarzschild radius of a single solar mass. This is why supermassive black holes, the kind that live at galaxy centers, have event horizons that can span billions of kilometers. Now here is something counterintuitive about the event horizon. It is not a physical surface. There is no wall there. No barrier you would feel or see as you crossed it. If you were falling toward a sufficiently large black hole, say, a supermassive one with 1 billion solar masses, the tidal forces at the event horizon would be gentle enough that you might cross it without feeling anything unusual at all. You would be inside, sealed off from the rest of the universe, and you might not even know it yet. The reason the event horizon feels so absolute, so final, is not that something is blocking your exit. It is that the geometry of space-time inside the horizon is structured in such a way that every possible path through space-time, including the path that light would take, curves inward. There is no direction out. You cannot aim yourself toward the exit, because there is no direction in which the exit lies. It has been removed from the geometry of your universe. Inside the event horizon, moving toward the center is not like moving through space. It is more like moving forward in time. You cannot go backward in time any more than you can choose not to move forward through the seconds of your life. Similarly, once inside the event horizon, you cannot choose not to move toward the singularity. It is your future. Inescapably. For an outside observer watching you fall in, the picture is completely different. Because light from you has to fight against the extreme curvature of space-time to reach the outside world, it becomes increasingly redshifted, stretched to longer and longer wavelengths as you approach the event horizon. From the outside, you appear to slow down, becoming dimmer and redder over time. You appear to freeze at the event horizon, fading to black, but never quite crossing. An outside observer would never actually see you cross the event horizon. You would simply fade from view. Meanwhile, from your own perspective, you crossed the event horizon a long time ago. This is one of the most profound features of general relativity. The same sequence of events can look completely different depending on the observer. This is not a trick of perception or a limitation of our instruments. It reflects something deep and real about the nature of space-time. The event horizon is the point of no return. And once something is inside it, the universe has lost it forever. Here is something remarkable. After a star many times more massive than our Sun, a star that spent millions of years fusing hydrogen, then helium, then carbon, neon, oxygen, silicon, and iron, collapses into a black hole. What information about that star survives? Almost none. A black hole is completely described by exactly 3 numbers. Its mass, its electric charge, its angular momentum, or spin. That is everything. There is nothing else. There is no record of what the black hole was made of, whether it formed from a star of iron or a star of hydrogen, from a cloud of gas or from a collection of rocks. There is no memory of the temperature, the chemical composition, the magnetic field configuration, or any other property of whatever formed it. Physicists call this the no-hair theorem. The name comes from John Wheeler, one of the most creative and prolific physicists of the 20th century, who popularized both the term black hole and the idea that black holes have no distinguishing features beyond those 3 numbers, no a hair. 2 black holes with the same mass, charge, and spin are physically identical, regardless of what formed them. This is deeply strange when you think about it carefully. In ordinary physics, information is conserved. If you burned every copy of every book ever written, the information in those books would not simply disappear, it would be encoded, in an incredibly scrambled form, in the pattern of smoke and ash and heat and light produced by the burning. In principle, with perfect measuring instruments and infinite computational power, you could reconstruct every word from the aftermath of the fire. Information is never destroyed. It is only transformed. But a black hole seems to genuinely destroy information. Throw 2 completely different objects into a black hole, a planet of iron and a planet made entirely of diamond, and the resulting black holes are identical, as long as the masses were the same. The information that one was iron and one was diamond has been erased. Or has it? This question, whether black holes truly destroy information or whether it is somehow preserved in a form we do not yet understand, is called the black hole information paradox. It is one of the most actively debated problems in theoretical physics, sitting at the boundary between general relativity and quantum mechanics. We will return to it in the final chapter when we discuss Hawking radiation, because that is where the paradox becomes truly acute. For now, consider the 3 things that do survive. Mass is the most intuitive. It is simply the total amount of energy, mass and radiation alike, that has crossed the event horizon. Mass determines the size of the event horizon through the Schwarzschild radius formula. Electric charge is theoretically possible, but in practice almost certainly negligible for real astrophysical black holes. If a black hole accumulated a net positive charge, it would preferentially attract negatively charged particles and repel positive ones, neutralizing itself over time. Real black holes are almost certainly electrically neutral or very nearly so. Spin, angular momentum, is the most physically interesting of the 3. Almost everything in the universe rotates. Stars rotate. Planets rotate. Galaxies rotate. When a rotating star collapses, its angular momentum is conserved. The smaller the resulting object, the faster it spins. Think of a figure skater pulling their arms in. As a massive star collapses, its rotation speeds up dramatically. The resulting black hole carries the angular momentum of its progenitor star, concentrated into an incredibly compact region. A spinning black hole is not merely a rotating version of a non-rotating one. As we will see in the next chapter, spin fundamentally changes the geometry of space-time around the black hole in ways that have dramatic physical consequences. But first, sit with the simplicity of it. The most violent, most extreme event in the universe, the collapse of a massive star, leaves behind an object that is described completely by just 3 numbers. In a universe of almost infinite complexity, black holes are the simplest objects that exist. In 1963, a mathematician from New Zealand named Roy Kerr solved one of the hardest problems in general relativity, finding the exact mathematical description of spacetime around a rotating black hole. Schwarzschild had solved the non-rotating case in 1916, and for nearly half a century no one had managed to solve the rotating case. The equations are ferociously complex. Kerr cracked them in a calculation that remains one of the great achievements of 20th century mathematical physics. What he found changed our picture of black holes profoundly. A rotating black hole, called a Kerr black hole, does not merely sit in space and attract things gravitationally. It drags spacetime itself around with it. Not metaphorically. Literally. Space in the vicinity of a spinning black hole rotates, the way water in a whirlpool rotates. This effect is called frame dragging, and it has been measured very, very faintly, even around the Earth, using gyroscopes on orbiting satellites. Around a rapidly spinning black hole, it is not faint at all. It is extreme. The region of space around a Kerr black hole where frame dragging becomes dominant is called the ergosphere. The ergosphere lies outside the event horizon. It is not the black hole itself, but a region of space surrounding it. Inside the ergosphere, the drag of rotating spacetime becomes so powerful that no object, not a rocket ship, not a light beam, can remain stationary with respect to the distant universe. Everything in the ergosphere is forced to orbit in the same direction as the black hole's rotation. Standing still is not an option. But here is the crucial distinction: the ergosphere is outside the event horizon. You can enter the ergosphere and still escape. You are not trapped inside it. That distinction turns out to be enormously significant. In 1969, the physicist Roger Penrose, who would go on to win the Nobel Prize in Physics in 2020 for his work on black holes, proposed a remarkable mechanism now called the Penrose process. He realized that if an object enters the ergosphere and splits into 2 pieces, and if the 2 pieces separate in just the right way, one piece can fall into the event horizon while the other escapes back out, and the escaping piece can carry away more energy than the original object had when it entered. Where does the extra energy come from? From the black hole's rotation. The infalling piece effectively has negative energy in the rotating frame of the black hole, and by falling in, it reduces the black hole's angular momentum and rotational energy. The escaping piece carries that extracted energy away with it. You have, in a very real sense, mined energy from the rotation of a black hole. This is not just a theoretical curiosity. Many astrophysicists believe that a related mechanism, called the Blandford-Znajec process, is responsible for the powerful jets of plasma that shoot out from some actively feeding black holes. These jets can extend for hundreds of thousands of light-years beyond the galaxy that hosts the black hole. They are powered, at least in part, by the rotational energy of the spinning black hole, energy being extracted from the rotation of spacetime itself. A spinning black hole is a store of energy, and it can give that energy back to the universe. The maximum possible spin for a black hole is called extremal spin, the point at which the ergosphere touches the event horizon and the rotational energy is at its maximum. Whether any real black holes reach extremal spin is an open question. Observations suggest that many supermassive black holes spin at very high fractions of the maximum, while others spin more slowly. Measuring the spin of a black hole from our vantage point billions of light years away is extraordinarily difficult, but it is something astronomers are actively working on. Spin is not just an interesting footnote to the story of black holes. It fundamentally shapes what the region around a black hole looks like, how it feeds, how bright it is, and whether it produces jets. Understanding spin is essential to understanding the full behavior of these objects in the real universe. Gravity does not pull all parts of an extended object equally. The side of an object closer to the source of gravity is pulled more strongly than the far side. This difference in gravitational force across the body of an object is called a tidal force. You experience a tiny tidal force from Earth at this very moment. Your feet are being pulled slightly more strongly toward Earth's center than your head is, but the difference is so small that you cannot feel it. As you approach a more massive, more compact object, tidal forces grow. They grow not just with the strength of gravity, but with how rapidly gravity changes over the size of your body. Near a black hole, this rate of change can be enormous. Imagine falling feet first toward a stellar mass black hole, one with 10 times the mass of our Sun, compressed inside an event horizon about 30 kilometers across. As you approach, the gravitational pull on your feet, being closer to the black hole, becomes significantly stronger than the pull on your head. This difference, the tidal force, begins to stretch you vertically. At the same time, the gravity field lines all converge toward a single point at the center, which means the gravitational pull on your left side is directed slightly to the right, and the pull on your right side is directed slightly to the left. You are being compressed from the sides as you are stretched lengthwise. Physicists gave this process one of the most viscerally expressive names in all of science: spaghettification. You are being turned into a long, thin strand of matter. Your body is stretched into something resembling a noodle, atoms at your feet moving faster toward the center than atoms at your head, the whole structure being drawn out into an impossibly thin thread as it spirals inward. Well before you reach the event horizon of a stellar mass black hole, you would be torn apart, first the chemical bonds that hold your cells together, then the molecular bonds within atoms, ultimately the atoms themselves. Now here is the twist that makes black holes even stranger. The severity of tidal forces at the event horizon depends on the size of the black hole, and larger black holes are actually gentler. For a stellar mass black hole, the event horizon is very close to the singularity. The gradient of the gravitational field is steep. Tidal forces at the event horizon are enormous. You are spaghettified long before you cross. For a supermassive black hole, one with 1 billion solar masses, the event horizon is billions of kilometers from the center. The gravitational field there is strong, but it changes relatively slowly over the scale of a human body. Tidal forces at the event horizon are quite mild. You could cross the event horizon of a sufficiently massive black hole without feeling anything particularly unusual. No discomfort. No tearing. Just a slightly unsettling awareness, if you knew what to look for, that the universe behind you was shrinking to a point. You would be doomed, inside the event horizon, falling toward the singularity, but you might spend hours or even days of your own proper time exploring the interior before tidal forces eventually became lethal as you approached the center. Tidal forces do not only affect hypothetical astronauts. They affect real astronomical objects, including stars. When a star wanders too close to a supermassive black hole, not falling directly in, but passing on a trajectory that brings it near enough, the tidal forces can overwhelm the star's own self-gravity. The star is torn apart. This is called a tidal disruption event. The shredded material from the star falls toward the black hole in a chaotic stream, eventually settling into an accretion disk and producing a dramatic flare of radiation, a burst of light that can briefly make a galaxy center shine much more brightly than usual. Astronomers have observed hundreds of these events. Some of them have been observed in real time, the galaxy center brightening over weeks and months as the disrupted star is consumed. By studying the light curve of these events, we can infer the mass and spin of the black hole doing the consuming, and learn about how black holes interact with their galactic environments. The universe, it turns out, is not short on drama. Let's clear something up immediately. Black holes do not suck. That is not a dismissal. It is a literal physical statement. The popular image of a black hole as a cosmic vacuum cleaner, endlessly sweeping up everything in its neighborhood, is misleading. Gravity follows an inverse square law. Double the distance from any object, and the gravitational pull drops to 1/4. At large distances, a black hole of a given mass exerts exactly the same gravitational pull as a star of the same mass would. If our Sun were magically replaced tomorrow by a black hole of identical mass, the Earth would continue orbiting exactly as it does now. Nothing in the solar system would be pulled in. We would all freeze to death, certainly, no sunlight, but not because of any sudden increase in gravity. The drama begins only when material gets close. Within a region called the innermost stable circular orbit, a few times the radius of the event horizon, there are no stable orbits. Material that wanders inside this region cannot maintain a stable circular path. It begins an inevitable spiral inward. Now, material rarely falls straight into a black hole. Almost everything in the universe has some sideways motion, some angular momentum, and angular momentum is conserved. Material cannot just drop straight down. It goes into orbit. But different bits of material have slightly different trajectories, slightly different amounts of angular momentum, and they interact with each other through collisions and turbulence. This interaction creates friction, and friction creates heat. The result is an accretion disk, a flattened structure of rotating, superheated gas and plasma orbiting the black hole, spreading outward like a vast glowing whirlpool. In the innermost regions of the disk, where the orbital velocities are highest and the friction most intense, temperatures can reach tens of millions of degrees. At those temperatures, matter does not glow in visible light. It glows in X-rays. This is the key insight. Black holes themselves are invisible, they emit no light. But the material falling into them can be extraordinarily bright. Some of the brightest sustained sources of radiation in the observable universe are not stars or galaxies in the conventional sense, but accretion disks around black holes. Quasars, the brilliantly luminous cores of distant active galaxies, are powered by supermassive black holes consuming material at prodigious rates, with accretion disks that outshine every star in their host galaxies combined by factors of hundreds or thousands. The efficiency of this process is staggering. Nuclear fusion, the process that powers stars, converts about 0.7% of the rest mass energy of hydrogen into radiation. It is already spectacularly efficient by everyday standards. It is what makes stars shine for billions of years. Accretion onto a spinning black hole can be 10 to 60 times more efficient than fusion, depending on the spin rate. For a maximally spinning black hole, roughly 42% of the rest mass energy of infalling material can be radiated away before the material crosses the event horizon. That is more than 50 times the efficiency of stellar fusion. This makes accreting black holes the most efficient energy-converting machines in the universe. Many actively feeding black holes also produce jets, narrow, highly collimated beams of plasma moving at very close to the speed of light, launched perpendicular to the plane of the accretion disk and extending for enormous distances. The physical mechanism is not yet fully understood, but magnetic fields threading through the disk and the spinning black hole play a central role. These jets can extend for hundreds of thousands of light years, blasting into the intergalactic medium and depositing enormous amounts of energy. In galaxy clusters, these jets heat the surrounding gas so effectively that they can shut down star formation across vast regions. The black hole at the center of a galaxy, eating its dinner, can shape the evolution of the galaxy itself and even its surrounding environment. Black holes do not just consume. They transform. They feed energy back into the universe in ways that structure the large-scale distribution of stars and gas across cosmic time. Stellar mass black holes, the ones that form from collapsing stars, ranging from roughly 5 to 100 solar masses, are one kind of black hole. But they are not the kind that dominate the universe on the largest scales. That distinction belongs to the supermassive black holes, entities with masses of millions, hundreds of millions, or even billions of times the mass of our Sun, lurking at the centers of almost every large galaxy in the observable universe, including our own. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, written Sagittarius A with an asterisk. It has a mass of about 4 million solar masses. Its event horizon, if we could see it, would span roughly 24 million kilometers. For comparison, the Sun's diameter is about 1.4 million kilometers. The event horizon of Sagittarius A star is about 17 times larger than the Sun. It sits approximately 26,000 light-years from Earth, buried behind enormous clouds of gas and dust that block visible light entirely. We cannot see it directly in the optical. But we know it is there, and we know its properties with extraordinary precision because of one of the most patient and meticulous observational campaigns in the history of astronomy. Starting in the 1990s, 2 independent teams of astronomers, one led by Reinhold Genzel at the Max Planck Institute in Germany, and one led by Andrea Ghez at the University of California, Los Angeles, began systematically tracking the positions of stars near the galactic center using infrared cameras that can peer through the obscuring dust. Year after year, decade after decade, they recorded the positions of dozens of stars in the central parsec around Sagittarius A star. What they found was extraordinary. The stars near the center were moving at hundreds and even thousands of kilometers per second, tracing tight elliptical orbits that all shared a common focus at a single point. One star, designated S2, has an orbital period of just 16 years. It completes an entire orbit around the galactic center in less time than it takes a child born today to finish high school and start college. At its closest approach, S2 passes within roughly 120 times the Earth-Sun distance of the central mass, moving at nearly 3% of the speed of light. From these orbital measurements, Genzel, Gez, and their teams could apply Kepler's laws, the same physics that describes the orbits of the planets around our Sun, and calculate the mass of the central object. The answer, 4 million solar masses, concentrated in a region smaller than our solar system. No known object other than a black hole can pack that much mass into that smaller space. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for this work, confirming the existence of a supermassive compact object at the center of our galaxy. They shared the prize with Roger Penrose, whose theoretical contributions we discussed earlier. But Sagittarius A star, impressive as it is a modest supermassive black hole. The galaxy M87, a giant elliptical galaxy in the Virgo cluster, about 55 million light-years from Earth, contains a black hole with a mass of 6.5 billion solar masses. Its event horizon spans a region larger than our entire solar system out to the orbit of Pluto. And even M87 star is not the largest known. Astronomers have identified quasars in the distant universe containing black holes with masses of tens of billions of solar masses, entities so massive that their event horizons span distances that would take light weeks or months to cross. How did these monsters form? This is one of the outstanding open questions in astrophysics. We observe massive black holes not just in the present universe but in the very early universe, within the first billion years after the Big Bang. These early quasars host black holes of 1 billion solar masses or more. How did they grow so large so quickly when the universe was so young? Several mechanisms have been proposed. Some black holes may have formed directly from the collapse of massive clouds of primordial gas in the early universe, bypassing the stellar stage and forming with thousands of solar masses from the start. Others may have grown through rapid and sustained accretion, consuming material at or near the theoretical maximum rate. Others still may have grown through mergers with other black holes. The truth is probably a combination of all these pathways, and current observations with next-generation telescopes are pushing back the boundary of what we know. What we do know is that supermassive black holes are not incidental features of galaxies. They appear to be intimately connected to the galaxies they inhabit, their masses correlated with the properties of the stellar bulges around them. Galaxy and black hole grew together, each shaping the other across billions of years. Understanding that coevolution is one of the central questions of modern astrophysics. General relativity, published by Einstein in 1915, made a prediction that seemed almost impossibly difficult to verify. When massive objects accelerate, and a massive here means truly massive, like neutron stars or black holes, they should produce disturbances in the fabric of spacetime itself. Ripples that propagate outward at the speed of light, stretching and compressing space as they pass. Gravitational waves. The problem was the scale. Even for the most powerful astrophysical sources imaginable, two black holes colliding, the effect of gravitational waves on matter here on Earth would be minuscule. A passing gravitational wave would stretch and compress a ruler by an amount roughly 1,000 times smaller than the diameter of a proton. A proton is already incomprehensibly small. 1,000th of its diameter is in a realm of smallness that strains the imagination. For most of the 20th century, detecting gravitational waves seemed essentially impossible. But a group of physicists, led eventually by Kip Thorne at Caltech and Rainer Weiss at MIT, developed a vision for how it might be done. Their idea became LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is, without serious competition, one of the most sensitive scientific instruments ever built by human beings. It consists of two identical L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by roughly 3,000 kilometers. Each detector has two arms, each 4 kilometers long. a laser beam is split and sent down each arm, reflected off mirrors at the end, and recombined. When a gravitational wave passes through, it stretches one arm and compresses the other, causing the laser beams to travel slightly different distances and creating a detectable interference pattern. The sensitivity required is extraordinary. LIGO must measure length changes of about 10 to the minus 18 meters across 4-kilometer arms. That is the equivalent of measuring the distance from Earth to the nearest star with an accuracy of the width of a single hydrogen atom. Achieving this required controlling and eliminating every conceivable source of noise, seismic vibration, thermal fluctuations of the mirrors, quantum noise in the laser light itself. It took decades of engineering refinement to get there. And then, on the 14th of September, 2015, just 2 days after LIGO had completed a major upgrade and resumed operations, it detected something. Both detectors recorded a brief, distinctive signal, a rising chirp of gravitational waves lasting about 0.2 of a second, arriving at Livingston 7 milliseconds before Hanford, consistent with a wave traveling at the speed of light from a specific direction in the sky. When the LIGO team analyzed the signal against theoretical predictions, the match was unmistakable. Two black holes, one with about 36 solar masses, the other with about 29, had been orbiting each other in a binary system, spiraling closer and closer over millions of years as they radiated gravitational waves. In the final fraction of a second before merger, they reached velocities of more than half the speed of light and produced a burst of gravitational radiation that swept through the universe and eventually reached Earth. The two black holes merged into a single object of about 62 solar masses. The missing 3 solar masses, 3 times the entire mass of our Sun, were radiated away as gravitational waves in roughly 1/5 of a second. At its peak, this merger was releasing more power in gravitational waves than the combined electromagnetic luminosity of every star in the observable universe. This event, designated GW150914, was the first direct detection of gravitational waves in history. It was also the first observational evidence for binary stellar mass black hole systems. And it confirmed, in the most direct way possible, a prediction that had stood unverified for 100 years. Kip Thorne, Rainer Weiss, and Barry Barish were awarded the 2017 Nobel Prize in Physics for the detection. Since that first event, LIGO, along with its European partner detector Virgo and the Japanese detector Kagra, has detected many more gravitational wave signals, from merging black holes, from merging neutron stars, and from mixed systems. Each detection is a new data point, a new test of general relativity in the most extreme conditions imaginable, and a new window onto a universe that was invisible to us before September 2015. Gravitational wave astronomy is now an established field. We have a new sense, a new way of perceiving the universe that does not rely on any form of light. We are listening to the universe now, not just looking at it. We had detected gravitational waves from merging black holes. We had tracked stars orbiting the black hole at the center of our galaxy. We had theoretical predictions of extraordinary precision and observational evidence from many directions. But we had never actually seen a black hole. Not directly. Not an image. Could we? The challenge is almost comically daunting. A black hole is, by definition, black. It emits no light. What we would hope to image is its shadow, the dark silhouette it casts against the glowing backdrop of its accretion disk and the light bent by its gravity from behind it. For the black hole in M87, 55 million light-years away, this shadow subtends an angle of roughly 40 micro-arcseconds on the sky. To give that number meaning, it is equivalent to trying to read a newspaper in New York from Los Angeles. No existing telescope, and no conceivable single telescope built on Earth, could achieve that resolution. But there is a technique in radio astronomy called very long baseline interferometry, or VLBI. By linking together radio telescopes spread across enormous distances and synchronizing their observations with atomic clocks, you can synthesize the resolving power of a telescope with an effective diameter equal to the separation between the most distant dishes. With telescopes spread across the surface of the Earth, you can approximate a telescope the size of the Earth itself. The Event Horizon Telescope collaboration spent years assembling exactly this kind of Earth-spanning network, linking together 8 radio telescope facilities on 4 continents in Hawaii, Arizona, Chile, Mexico, Spain, Greenland, and Antarctica. Each site observed simultaneously, recording data at rates that produced petabytes of information, so much data that it could not be transmitted over the internet and had to be physically flown, on hard drives, to central processing facilities. The observations targeted M87 star were conducted in April 2017. 2 years of data processing, calibration, and verification followed. On the 10th of April, 2019, at coordinated simultaneous press conferences held on 4 continents, the Event Horizon Telescope collaboration released the result. An image. A glowing orange ring, slightly asymmetric, with a dark central region. The ring was the superheated plasma of the accretion disk, its light bent by the black hole's immense gravity into a near-circular structure. The dark center was the shadow of the event horizon, the region from which no light escapes. The asymmetry of the ring was not an artifact. It was a prediction. On the side of the disk where material moves toward us, relativistic effects brighten the emission through Doppler boosting. The image matched the predictions of general relativity with striking precision. From the angular size of the ring and the known distance to M87, the team calculated the mass of the black hole, 6.5 billion solar masses, consistent with previous estimates. It was the first image of a black hole in human history. After a century of theoretical prediction, after decades of indirect evidence, we had finally seen one. Or at least, we had seen its shadow, the shape of its absence, silhouetted against the light it could not hold. 3 years later, in 2022, the Event Horizon Telescope released a second image, Sagittarius A star, the black hole at the center of our own Milky Way. This was technically more challenging than M87 star. Our galactic center black hole is much smaller, and its accretion disk varies on timescales of minutes, requiring sophisticated techniques to average over the variability. But the result came. A glowing ring, strikingly similar in structure to M87 star, from a black hole 4 million times the mass of our Sun, 26,000 light-years away. We have now directly imaged the 2 most studied supermassive black holes in the sky. And both images confirmed what general relativity predicted. Einstein, who spent the last decades of his life doubting whether black holes were real, has been vindicated in the most spectacular way imaginable. For a long time, black holes seemed permanent. Once matter crossed the event horizon, it was gone. The event horizon could only grow. It grew whenever something fell in, and it never shrank. Black holes, it seemed, were one of the few truly irreversible features of the universe. Then, in 1974, Stephen Hawking sat down and did a calculation that nobody expected. He applied the principles of quantum mechanics to the vicinity of a black hole's event horizon. And he discovered something that turned the prevailing picture on its head. Black holes radiate. To understand how, you need a brief detour into the quantum vacuum. In quantum mechanics, empty space is not truly empty. Due to the Heisenberg uncertainty principle, pairs of particles, a particle and its corresponding antiparticle, can spontaneously appear from the vacuum, exist briefly, and then annihilate each other and disappear. These are called virtual particle pairs. They borrow energy from the vacuum for a moment and then return it. In flat, empty space, they always annihilate. The net effect is zero. But near the event horizon of a black hole, something different can happen. If a virtual particle pair appears just outside the event horizon, there is a chance that one of the pair is captured by the black hole before the pair can annihilate. The other member of the pair now has no partner. It becomes a real particle. It escapes to infinity. From the perspective of a distant observer, the black hole has emitted a particle. The black hole is radiating. The energy for this radiation has to come from somewhere, and it comes from the black hole's mass. The infalling partner carries negative energy in the black hole's frame, effectively reducing the black hole's total mass. Over time, an extraordinarily long time, the black hole loses mass through this process and eventually, in principle, evaporates entirely. This is Hawking radiation. The temperature at which a black hole radiates is inversely proportional to its mass. A more massive black hole radiates at a lower temperature. A stellar mass black hole of 10 solar masses radiates at a temperature of about 6 billionths of a Kelvin. The cosmic microwave background, the thermal afterglow of the Big Bang, has a temperature of about 2.7 Kelvin. So currently, every stellar mass black hole in the universe is absorbing more energy from the cosmic background than it is radiating through Hawking radiation. They are growing, not shrinking. Only in the far future, when the universe has expanded and cooled enough that the cosmic background temperature falls below the Hawking temperature of these black holes, will they begin to lose mass. And even then, the timescale for a stellar mass black hole to evaporate completely is roughly 10 to the power of 74 years. The current age of the universe is about 14 billion years, roughly 10 to the 10th power. A stellar black hole's evaporation timescale exceeds the age of the universe by 64 orders of magnitude. They will evaporate, but not anytime soon. Hawking radiation raises a question that has occupied theoretical physicists for 50 years and has not yet been resolved. If a black hole formed from a star with a specific, definite quantum state, every particle in that star with specific quantum numbers, and then the black hole evaporated via Hawking radiation, where did that information go? Hawking's original calculation suggested that the radiation is purely thermal, purely random, carrying no information about what formed the black hole. When the black hole is gone, the information is gone. But quantum mechanics forbids this. One of the foundational principles of quantum theory is that the detailed quantum state of a closed system is always preserved. Information is never destroyed, only scrambled. A process that starts with a star in a specific quantum state and ends with a cloud of featureless thermal radiation has violated one of the most basic rules of quantum mechanics. This is the black hole information paradox. It is the deepest, most direct collision between general relativity and quantum mechanics that we know of. Resolving it will require, most physicists believe, a complete theory of quantum gravity, a theoretical framework that fully unifies quantum mechanics and general relativity. Such a theory does not yet exist. Some proposals suggest that information is secretly encoded in subtle correlations within the Hawking radiation, imperceptibly scrambled but not destroyed. Others suggest that something fundamentally new happens at the end of the evaporation process. Still others invoke the holographic principle, the idea that all the information inside a black hole is encoded on its surface, on the event horizon itself, in a way analogous to the way a three-dimensional scene can be encoded on a two-dimensional hologram. None of these proposals has been fully worked out or accepted. The paradox remains open. And it is an extraordinarily productive open question, one that has driven some of the most creative theoretical physics of the past several decades, including the development of string theory, loop quantum gravity, the holographic principle, and much more. Black holes, it turns out, are not just extreme astrophysical objects. They are theoretical laboratories, places where the deepest tensions in our understanding of the universe become visible. They are where physics goes to break down, and where it goes to be rebuilt. Let's bring the whole story together. Black holes begin with violence. A massive star, one with more than roughly 20 times the mass of our Sun, burns through its nuclear fuel over millions of years, fusing ever heavier elements until it reaches iron, the dead end of fusion. With no more outward pressure, gravity wins in milliseconds. The core collapses, producing a neutron star or, for the most massive cores, a black hole. The outer layers of the star are blasted away in a supernova. What remains is a singularity of effectively infinite density, surrounded by an event horizon, the point of no return. The event horizon is defined by the Schwarzschild radius, the distance at which the escape velocity equals the speed of light. Crossing it is a one-way journey, not because of any physical barrier, but because the geometry of space-time inside it allows only one direction, inward. What survives this collapse is almost nothing. A black hole is defined solely by its mass, its electric charge, and its spin. All other information about what formed it is lost, or at least hidden, giving rise to the no-hair theorem and the information paradox. Spin matters enormously. A rotating black hole drags space-time around it, creating an ergosphere from which energy can be extracted via the Penrose process. Spin powers the jets that reshape galaxies and the brightness of quasars. Tidal forces near small black holes spaghettify infalling objects, stretching them vertically and compressing them laterally, long before they reach the event horizon. For For supermassive black holes, these forces are gentle at the horizon, making the crossing imperceptible. Accretion disks, the whirlpools of superheated plasma that form as matter spirals inward, make black holes some of the brightest objects in the universe, converting up to 42% of infalling mass into radiation. They power quasars, produce X-ray binaries, and drive jets that heat the intergalactic medium. Supermassive black holes, with masses from millions to tens of billions of solar masses, inhabit the centers of almost every large galaxy. Sagittarius A star, for million solar masses, lives at the center of our own Milky Way. M87 star, 6.5 billion solar masses, was the first to be directly imaged. That image, the orange ring released by the Event Horizon Telescope in 2019, was a historic milestone. A century after general relativity predicted them, we finally saw the shadow of an event horizon. Confirmed by the image of Sagittarius A star in 2022. The detection of gravitational waves by LIGO in 2015, from the merger of two black holes over 1 billion light-years away, opened an entirely new branch of astronomy, one that doesn't look at the universe but listens to it. And black holes do not last forever. Hawking radiation, the slow quantum evaporation of mass from a black hole through virtual particle processes near the event horizon, ensures that every black hole will eventually disappear. But it will take unimaginably long timescales. And the process raises the deepest unsolved question in theoretical physics: where does the information go? That question, the information paradox, is not just an abstract puzzle. It is a signpost pointing toward the next great synthesis in physics. A theory of quantum gravity that reconciles the two pillars of modern physics in the most extreme environment the universe provides. Black holes are where everything we know about the universe is tested, and where much of what we will learn still waits. That is the full story of black holes, from the death of a massive star to the last slow evaporation of the final black hole in a cold, aging universe. But honestly, we barely scratched the surface. There are entire chapters of this story we did not have time to open. Primordial black holes, hypothetical black holes that may have formed in the very first moments after the Big Bang, and which some physicists believe could account for part of the universe's dark matter. The firewall paradox, a sharper and more disturbing version of the information paradox that emerged in 2012, suggesting that the event horizon might not be the peaceful boundary we thought it was, but something more like a wall of lethal radiation. The holographic principle, the idea that everything inside a black hole, and perhaps everything in the universe, is encoded on a two-dimensional surface. And the question of what actually happens at the singularity, whether it is a real physical feature of the universe or a sign that our current theories simply break down, and something new and stranger takes over. The universe is not short on mysteries. And black holes are where the deepest ones live. If this video gave you something to think about, if it changed how you see the universe even a little, please take a moment and hit the like button. It genuinely helps this channel reach more people who are hungry for exactly this kind of deep, honest exploration of science. Subscribe if you haven't already. Every video on this channel is built the same way this one was, starting with the real science, going as deep as it deserves, and not stopping until the story is told properly. And leave a comment. Tell me which part of today's story hit you hardest. Tell me what you want to explore next. The information paradox? The holographic principle? Neutron stars? Dark matter? The Big Bang? This channel goes where the curiosity goes. And your curiosity drives it. I'll see you in the next one. Keep orbiting the truth.